Okay, good morning and welcome to this seminar. I am Enrique Argones Rúa, as you know. I work as a researcher here in COSIC. And today we'll talk about a paper we submitted to the workshop in Information Forensics and Security last year. It was celebrated on December 2024 in Rome. And it is about using biometrics into security solutions, into authentication protocols, using this primitive, constructions already strengthened fuzzy extractors, using some very cool name error correcting codes called the turbo codes, and very special modality of biometrics, this finger vein authentication. So this work was done in collaboration with some colleagues from Roma Tre University, Dr. Emanuele Majorana and Professor Patricio Campisi. And I would like to thank them from here for this collaboration. Okay, so first, I know this slide has been shown to you by many in different occasions with different purposes, but it is the basis of authentication. So we can only authenticate people by 3 different means, but things they own and they exclusively own, like, I don't know, like a physical key. For instance, I have my bicycle key here in my pocket. The thing is that this is the third one. So there is something bad about the things you have, which is that they can be lost. About passwords, they can be forgotten. You remember these emails coming in September in my case, telling me, please change your password for ESAT or Q11 or whatever. And then the very next login attempt by me always is a mistake. I always forget my keys, and I am a disaster for this. But okay, let's see, biometrics, they are not perfect. They are, first, they are more cumbersome to compare, because it is not the same to compare a password, which should always be bit by bit the same. So all the presented information needs to coincide. And something different is with a biometric reading, because they will always be noisy, they will always be slightly different, and it is not easy to know how this difference is. How different is it? What are the factors? Illumination, like the minions would say, is the key for some. How do we model the distance between two biometric traits? And also, and pretty important, is the privacy aspect. So I do not want people to know that I am using this service, whatever service it is. But if I store my biometrics in their servers, unprotected, anybody with access to that can, first, get my biometrics, second, link me to that service. That is a big privacy issue. And then even it would have security implications, because the hacker, having access to that data, could try to use that data with access purposes in different services. So there are many things which can go wrong with biometrics. That is why we need this type of technologies, the biometric template protection technologies. Are you familiar with any of them? Do you know what this can be? I guess, even from, I don't know, previous seminars I gave here. Come on, the old ones, you know. Okay, there are basically, there are even several ways to classify these template protection approaches. One of them are the cancelable biometrics. So basically, by changing the parameters of some non-invertible transformations or changing the salt, you can make different versions of the same biometric template. and they should not be enough to get back to the original biometrics, etc. But there are several strategies to attack those, and this is not the subject of this presentation. So let's focus on biometric cryptosystems, which are a much more natural way to integrate biometrics into cryptographic protocols. I think they are much easier to understand by, for instance, by cryptographers. Huh? What they do is just you give these cryptosystems, you give them a sample of your biometrics, and it will generate, commit, bind a cryptographic key to it. It will also produce public helper data, which is going to be useful for authentication purposes, but should not disclose anything about the biometrics or the key. The key that is the secret at the end. And a good example of such cryptosystems are the fuzzy extractor. I guess this sounds familiar, fuzzy extractor, maybe not. Come on, for you, yeah. For you it is familiar. So let's see. As a black box, the fuzzy extractor is just these two constructions, the generate, which is a randomized construction. So every time you use it, it will generate different outputs. It is this kind of magic thing, which uses randomness. It has this input, the biometric binary representation. Could also be a model instead of one sample, but it doesn't matter. And then it produces a secret string. This is basically something that you can use in any cryptographic protocol as a symmetric key that identifies this user. Or you can use it to generate private, public key pair, whatever. But it is a secret string. And a public string, which any adversary could have access to, but it would not pose a threat. It poses a threat, but we'll see to what. And then there is this reproduce, which has this input, the biometric binary sample, which I put here Q sub J, which means J could be equal to the same user, to I or not. Let's assume the public string is the one generated by the generate procedure. And then if this binary representation of the biometric is close enough to the one presented to the generate, then it will produce the same secret string. Otherwise, it will just produce nothing. It will not react. So that, well, you can think like it will say just no. Okay. So what is the problem? This is a great construction. Okay, that was just an idea. This is one implementation of it, a concrete one, which is called the fuzzy commitment. And it relies on this error correcting code. So basically, how does it work? The generate, this randomized procedure, it produces a random secret string, which is great because it is totally unrelated to biometrics. It is just a random thing that goes out. And it uses that as an input to this error correcting code encode. So what you get, this W there, is a code word. So that code word is XORed with this binary representation. And what you get, this F, is a committed biometric. Well, it's just the committed value of the biometric with this code word. Then you just concatenate the hash of the random message with this committed thing, and you get this public string. So when you go to the reproduce and you provide something similar, let's imagine that the difference between this and this is a vector with Hamming weight less than the error correcting capability of the error correcting code. In that case, then when you perform this XOR here, this will be very close to this one, which means that this will produce exactly the same message. So this message is the same as that one. Therefore, its hash is the same, and then you can output the secret string. But what happens if it is very different? Let's imagine the Hamming weight of the difference between QY and QJ is too big. In that case, this code word will be closer to another code word, or maybe even not decodable. So in that case, this will be different. Therefore, nothing will be said at the end. But what is the problem with this? Basically, the helper data, this public string, it contains this code word. And the problem with that is that if you generate again with the same biometric, if you look at both public strings, the difference between them, the difference between this F and the other F will be exactly one code word. And the probability for that, if the biometric is random, would be negligible. That means that if you use the same biometric, the helper data, you can link both of them. This is a linkability issue. And even if the same user provides a slightly different biometric, the difference between both committed values will be very close to a code word. It doesn't remove linkability. So both public strings would be linkable to the same user. This is a privacy issue. How do we remove this? And also, it is not a flexible construction in the sense that, okay, it was designed by a cryptographer. It had somehow biometrics in mind, but as you see, it assumes biometrics kind of are binary things. Are they? No, we know they are not. So we need to do something with the biometrics in order to get these binary strings. And maybe in that we can get some advantage. So this, I think we already talked about the inputs and outputs of this strengthened construction. No, we are already with the strengthened construction, sorry. So this is what we can do. We can add a second factor authentication. Anyway, the multifactor authentication is now the standard, as we saw in the introduction. So let's do it properly anyway. So the key is that now you have this additional fixed string inputs both to the generate and reproduce constructions, as you can see. And what are they used for? It is pretty simple. Inside this generate and the reproduce construction, now we put this metadata extractor and this parameterized mapping. The metadata extractor will be in the generate, and this parameterized mapping will be in the reproduce. There will be some error correcting code inside this, this extractor. And what happens is that this metadata extractor gets some data from the biometrics that will assist the other one, this parameterized mapping construction later in the reproduce, to get exactly the same secret string in the case that it comes from the same user. Otherwise, it should spit nothing. So this construction should say nothing. So yeah, but how is it done? These boxes are very nice, but how do we do this? And then the use of this fixed string, it is pretty simple. We just encrypt with this all the public helper data. So no linkability issues anymore. But Anyway, if you get access to this second factor, and you can decrypt this helper data, you should not get too much information about the biometrics. So in that case, we know there will be linkability, but there should not be reversibility. There should not be a security issue related to that disclosure. So let's see how this can be done. So in this work, what we did basically is to design and to evaluate strengthened fuzzy extractors using a specific type of error correcting code, which is the turbo codes, and an appropriate biometric modality, which is the finger vein recognition use case. Usually when you choose an error correcting code, it doesn't matter whether it is cool or not. What matters is that the optimal error correcting region for this code should match the signal to noise ratio that your modality provides, and this is the case. It is a good match for this type of codes. So the thing is that we designed these strengthened fuzzy extractors in a user-independent way, which was the standard before. Then we used the user-dependent bit loading, and also user-dependent bit loading and feature combination. So let's see what we are talking about. So in the enrollment phase, what we do with this new construction is that we first need to transform the biometric readings. So you have let's imagine just a row of real numbers, and you have to transform them into a digital constellation domain. It is not that we are going to transmit it through a communication channel, but it doesn't matter. We are doing something conceptually equivalent to that. Then we must bind this this biometric to some randomly generated digital constellation symbols. How do we generate them? First, we need to generate a random string, this B below. Then we generate a code word using whatever error correcting code, and then we encode that in the constellation domain. And then we bind it with a biometric reading. So that is what we do in the enrollment. And then the helper data that we would have would be this, this committed vector V and the secret string or its hash. So just something to check the authentication result. How do we do this binding thing? So here, what we have here is the 8 PSK constellation. I guess most of you are familiar with this. So basically, we encode symbols in the face of a complex number. This complex number will be in this unit circle. So there are, in this case, 8 possibilities, and we encode also this biometric QI. We encode it to this angle, UI. And intuitively, we know that in order for this not to provide any information about the symbol that is being encoded, we know that this face should be population-wise uniform. So that I give you this value, and then you would not know anything about which symbol it comes from. Because if you pick this Q from the population, you would get a uniform in this circle. And how this is done usually, well, you can, for instance, use the cumulative distribution function of this sample multiplied by 2 pi and a random polarity. So +1, -1. So this is usually what can be done. More formally, then in verification, you just need to unbind the biometric and the code. And hopefully, the biometric representations will be close enough and you will get the same key, the same secret at the end. More formally speaking, this binding thing. As I already said, these binding and unbinding functions should be designed to avoid information leakages from this committed value. And this means that indeed the population-wise, this value added from the biometrics, this UI should be uniform, which does not mean always to use the cumulative distribution function, but that is the most efficient regarding signal-to-noise ratio. There would be other possibilities. So, for instance, instead of using this CDF, which will give this distribution for the committed value, you could use, for instance, a triangle that resembles the convolution of the CDF with itself. If you do that, what happens is that you spread the symbol, but at the end, since there is this modulus operation, this modulus 2 pi operation, at the end you will get anyway a uniform. But you're spreading the symbol, you're making your signal to noise worse. If you are using a fuzzy extractor, that could be a reasonable option anyway, because you reduce linkability. But if you're using a strengthened fuzzy extractor, the best you can do is to use the uniform directly, the CDF, for getting this uniform, so that your signal-to-noise ratio remains very small. Very big. So, now, for binding and unbinding, you can use many different functions, but the simplest one is just using addition and subtraction. If this is the case, then, as you can see, what we get at the end, after unbinding, is the original symbol plus the difference between the biometrics in this domain, in this CDF domain. So this is what you get. If this is close enough to this, then you should be able, with your error correcting code, to decode this guy. But then, how many bits do we put in these constellations? It depends on how noisy each of the biometric features is. But this can be something you measure population-wise. There could be a feature which is very noisy for everybody, but you could also try to make an estimate for the user-dependent value of this signal-to-noise ratio. There could be some features which are better for some people than for some other. Feature which is not very present, the distinctive side of it could be like too wide, too noisy for some people, but for some other it could have a very distinctive value. So anyway, in the case that we are not using user-independent information, like in a fuzzy extractor instead of the strengthened, if you are using only user-independent information, then we need to rely for this bit loading for how big these constellations are on the intra-class variability population-wise. So you see how much the noise is for each of the features for the whole population, instead of looking only to a given user. So then you would have only this helper data, this public helper data, which is the committed biometric, the hash of the random secret string, and then the polarity vector. I am not putting here the bit loading information because it is population-wise. So for everybody, it would be the same. So that is a system design string. It is not part of a given user's helper data. But since we have this Strengthened Fuzzy Extractor, we can indeed incorporate user-specific, user-dependent information. Like this user-specific variability information can be added now to this construction. If we just do that, then our helper data would be this one, where S encodes the size of these constellations. And we can do, on top of that, we can also try to, instead of using just the features as provided by the biometrics module, we can try to combine them in such a way that, you improve the signal-to-noise ratio of some features. So imagine you have, you use 4 features to get 3 less noisy features. So that you combine these features in a way that you improve, you diminish the bit error rate at the end. This will have a benefit in terms of effective key length, or hopefully it will. But how do we combine? What do we do? To combine features and get a benefit out of it, what we should do is to minimize the standard errors for the genuine attempts. So the difference between 2 readings for the same person when you combine these features should be smaller than the original feature ones. So you can think of this problem as just minimizing the mean squared error rate for the genuines with respect to the imposter ones, and this quantity would be just like this. So here the user is the same, so that is the difference for the genuines, and here the user are different. This is for the impostors. Then W is the weights vector. And this here are the mean of the features for the user. The covariance matrix. The covariance matrix for this should be population-wise, and this should be user-wise. I think this is a mistake in the equation. But anyway, there is a way to compute. If you follow these equations, there is a way to compute the optimal weight vectors for this. If you remember your linear algebra, it can be done just like this. And there is a problem with this, which is the size of the matrices. The size of the problem is too big. Usually you only have some enrollment samples. Let's imagine 5. You cannot then compute huge matrices and try to get invertible ones with so little input data. So then what you have to do is to work block-wise. So you make small blocks, and you should design which features you select for each block. It is not, you do not have a, you do not have the freedom to choose randomly. You should get each group more or less equally reliable than the other ones. There are ways to do it. In the paper they are explicit, but anyway. So at the end what you get is this, projected features. This matrix will be block-wise, diagonal. There will be most of the coefficients in the general M will be 0. So it is only done with very small blocks, this matrix. So in this case, the helper data is a bit more complete. It has this combination matrix. It has the user-specific bit loading and everything else that the user independent fuzzy extractor has. Okay, so this is how it looks, this helper data constructions. It is not important to know its structure. I think you are not going to design Strengthened Fuzzy Extractor just when you leave the seminar, so you can always read it in the paper, how it is done and what everything means. So let's talk now about the fancy biometrics we are using. It is just the finger veins, so I don't know if, I remember when I was a kid and in my parents' building elevator, the button was red and I could see my veins through it in the finger. This is just the same, but instead of using a visible red light, they are using infrared, so they get even better images like this. A bit creepy, but these are human fingers and from different individuals, and if you were close enough, you would see how different they are. They are very different. What do we use to distinguish them? How do we build this metric space? We just use deep learning machine, which is trained to recognize something else, like cats, tables, chairs. So we just use this transfer of knowledge from one system that can distinguish whatever to this. Because something that distinguishes whatever should be able to distinguish this. And it does, and it does pretty well. But if we pay attention to these constructions we have, we should get something in the input which is more or less independent. Otherwise, we should deal with this dependency inside. Since we do not want to do that, we do this robust independent component analysis, so we get almost independent features in the input of our construction. Okay, so at the end, each finger will be just a set, well, a vector of 196 almost independent real numbers. That is a finger for us. Of course, we made the experimental protocol with a training set for this last layers of the neural network training and the RICA training. And then we have an evaluation set that we divide in validation and test set. The validation is basically to decide which parameters are the best for our system and things like that. And the test is for the a priori performance measurement in our system. This is very important, that we do not cheat when we do these experiments. The results should be always a priori. We use, as we already said, these turbo codes. I I don't know how familiar, this seminar is not about turbo codes, but anyway, they are so cool that something has to be said about them. Huh? So basically, in these turbo codes, there are these two convolutional codes. You know what a convolutional code is? Huh? No? Yeah, come on. Let's ignore that, yes? And anyway, these turbos here, it is just symbolizing that this decoder will get information that is fed into this other decoder, which would not be accessible to this decoder by itself, but it tells something important for him to improve the decoding probabilities, the success probabilities. And then this does the same, exactly the same. It can get information which is useful for this one. So that is why they are called turbo codes, because each of them helps the other one in an iterative process so that at the end they correct as many errors as possible, well, as they can. Okay, so the codes here are 32 states, so only 5 bits of state, each code. The rate is 1/3, which means that each code produces, for each input bit, 1 output bit plus 1 redundancy bit. And since the input is the same for both codes, we only include it once. We don't need to include it twice. So that is why the rate is 1/3. And then we evaluate the best configurations we obtain in the validation set, we evaluate them in the test set. And we look at different working points of the constructions. The most important ones are, I would say, the 1% false rejection rate and the 5% false rejection rate. You know what false rejection rate, false acceptance rate are? I guess you do. So we just move on. And what do we report? On what basis can we compare the different systems we have? Well, we will report here the false rejection rate and the effective key lengths. Why are not we reporting also the false acceptance rates? Because the false acceptance rates are, the probability of them are of this order, 2 to the minus k. And you can believe me, you will see the numbers that this number is too small in comparison to the size of the database, therefore we will get a 0%. We are not claiming that we get 0% false acceptance rate. That is absurd, because by chance you will get the same key eventually. By random number generation theorems, you would get this kind of rate, which is too small. So we are interested in comparison in terms of false rejection rate and the effective key length. So how many bits can we extract with the constructions? And that is key. Because when you think about security, as cryptographers, you think in the number of bits, don't you? No? Yes, I think so. And you're right. The more bits, the better. So we compare these systems, the user-independent, where no user-specific bit loading is used, and no user-specific feature combination is used. So this goes like, yeah, I don't know anything. I am a fixed system for the full population. And let's see what I can get. But we can also put this bit loading vector, which is user-dependent, and also on top of that, we can try to improve the features we fit to the construction by previously combining them. So the bit loading function is related in theory to this very beautiful Shannon formulas of the channel capacity and But at the end, we have to use an empirical one where we assume that we will get a more noisy version of the distributions in the test set. So therefore, we have a parameter that we need to adjust, and that is done using the validation set. And also, there are many different ways to combine the features. Huh? So we use these different schemes, and we will compare them. So this means that, for instance, the 3/4 means that we have 4 input features, and then we have 3 output features. So the matrices will reduce the number of output features by this relation, 3/4. So instead of 196, we will have 3 times that divided by 4. Number of features, combined features at the end. So for 1% false rejection rate, this means that we set the false rejection set rate in the validation set to 1%. And we see what is the system that gets that for each of the configurations. In the case of the user independent, when we evaluate the best system getting less than 1% false rejection rate, we get keys this long, 37 bits. How good do you think this is? Would you trust it? For what? No? Well, it depends. For what? I mean, your credit card PIN is much shorter. Huh? Okay. Yeah? Yeah, so please.
2 to the 37 is more than the people in the world, so probably fine, right?
Yeah, probably. But you would never use such a symmetric key for anything in a cryptography protocol. So you could use this for some things, but not for everything. When we use this user-dependent bit loading, honestly speaking, we were not expecting this kind of improvement. I mean, we are almost doubling here the key size. By just taking into account that for you, this feature is more robust than for her. And we know this for you, and we know this for you. So we can make your keys longer using this information. And then if we, on top of that, we do these feature combinations also adapted to the users, we can even improve that by 10 bits. These keys are already kind of in a good crypto length, I would say. And this is for false rejection rate less than 1%. So you are bothering people, genuine users, less than 1% of the times. Okay, unless you are bothering the same person all the time, this should be acceptable. And in any case, it would be acceptable for everybody except for that person. So, what happens when we are a bit more flexible regarding usability and we allow for this 5% false rejection rate? Yeah, in the case of user independent, now we are talking, we have 69 bits. This is for biometrics already a pretty nice number. But then again, if we allow to use this user-specific data, we have this much bigger. This is serious security, I would say. Should we believe that these 114 and 105 are actually equivalent, bits equivalent, totally equivalent to these symmetric crypto primitives? Only if we are very sure about the statistical properties of everything in the system. So careful with that. You have the paper, you can go through and then tell me whether you can believe in these numbers. And this is the distribution of the effective key length for the population we have. I am sorry we don't have millions of people here, so this data set is very small, and anyway you can visualize something. That, okay, this straight line here is for the user-independent system. So you can see this 37 bits security we had in the first table. And that's it. That's what you get for all users. So it's just a straight line. That is the effective key length you get for that. And for the user-dependent bit loading, it is the dark one. Yeah, we have this mode here in the distribution, which was a bit unlucky. But anyway, most of the keys have pretty good values, and only some of them fall in this area, which is even worse than not using user-specific information. And for the other one, the user-dependent bit loading plus combination, we plotted here the best one. You can see that this mode here close to this boundary disappeared, so it is like going like that. Then it keeps here, goes up, goes down. But anyway, there is a tiny proportion of the people here with smaller keys than in the user-independent case. So after watching at the results, I guess we can discuss something about those. So we can see in general that for most of the people, you would get a much bigger key size. And in average, you get almost double the key size for some of the use of the working points. And when you use feature combination, you get better specifically for small false rejection rates, which are the most convenient working points. Would be better to never reject a genuine user, isn't it? So for those working points, if you also use the feature combination, you get better results. And what about these poor users that get smaller key sizes in the user-specific Strengthened Fuzzy Extractor? What do we do with those guys? Because before we had 37 bits for everybody. But now I tell that for you, I'm sorry, but I am only giving you 30. So, do you think I am discriminating you somehow? Because maybe what happened before was that since the system was not so flexible, I was rejecting you many times when you were trying to use the system. Because your biometric cannot hold this many bits. Because, I don't know, maybe you have something strange in your finger, whatever, or you move it when it has a behavioral component as well sometimes. So maybe it is not possible to give you a longer key, and I was rejecting you many times. Now I gave you a shorter key, but probably I am not rejecting you as much. So this type of schemes usually allow to give more or less the same problems to everybody, instead of, because they are user specific. Okay, so just the conclusions. We designed these new constructions based on this type of codes. They are enabled by using these two factors. Without these two factors, there will always be problems regarding privacy or security. So careful with these biometric protection schemes, which are monofactor, because they will have problems. By doing this, yeah, we get much bigger keys associated with the biometrics. And we would like to explore for using this in other modalities or how to include other modalities into this. It is not so simple because some modalities will not have the same kind of signal-to-noise ratio. For instance, face is much more noisy. So if a code is good for face, it is not good for this, and the other way around. So some things need to be done in that case. And I think that's it. So please, if you have any question, go ahead.
I guess I'm wondering about the data set you use, because I think it's
The what?
the data set you use.
This Stumla dataset. It is public. It is public. So you can download it. I do not remember whether you need to register in the website or something like that.
I'm wondering, like, I guess it contains these
Images.
readings for multiple people,
Sure.
and then for some people, multiple of these readings, because otherwise you can.
Sure. Yeah. Yeah.
But then I'm guessing for like the user specific stuff,
Yeah.
if I take 5 readings now
Yeah.
or 5 readings spread over 1 year,
Yeah. It is not the same.
yeah, this will also influence, I guess, the result you get for how many bits eventually you get.
Sure. Yes. 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 If you do consecutive readings, even worse, if you ask the user to not move the finger, what you get is not representative. So you should do this in independent sessions. So yeah, this user-specific thing indeed has the problem that it is either you make it dynamic, so at the beginning you just register with one thing, forget about user-specific stuff. It will be the basic generic population-wise system, 37 bits, rigid. But come on, you only gave me one reading. What do you want me to do? So then when you later give more readings, you can enable these kind of schemes. And in the case of the dataset, they are different sessions. Readings from the same, they read 2 fingers, I think, per person. So in each session, they ask to place one finger and then the other. And they repeat different days. And at the end, you have 6 sessions per finger. We use each finger as a person. So with me, they would have 2 persons, this and that. I mean, they are totally independent. You wouldn't know whether they come from the same person or not, so there is no problem. So yeah, and I don't know what else would you like to know about this data set?
That was my main question.
I mean, I did not process the data set myself. This work was done by our Italian colleagues, by Patricio and Emanuele's team.
Maybe one more thing that I think about it, like the data set is really pictures like the ones you showed on the slide.
Sure, yeah.
How do you avoid that the neural network takes the length of the finger into account? Or is that
Sorry?
like, it's not showing the full finger.
Yeah, it is not the full finger. It is, this is,
I was just wondering, like, is it allowed to take like the dimensions of the finger into account instead of just?
no, it is not in this case. I mean, everything is designed to get a fixed length representation at the end. And things like that, like what is the size of the image, you could input it to the system, but I can tell you it wouldn't improve too much anything.
No, but I would even expect it to be worse. Like there's examples of neural networks finding or using features that we don't want it to use. And so I'm wondering, is there something here that the neural network could be using that you don't want it?
Yeah.
Are they all nicely numbered?
Look.
Like number 1, number 2.
I mean, for sure, this has no relation to the finger, and this is not discriminative, or this. because it is not part even of the finger. So what happens? You have this neural network, which is a CNN, a very deep and complex with, I don't know how many weights. I don't even want to know. But it was tuned for distinguishing things in general. So it is good. But on top of that, we put a fully connected layer. I am not even sure whether one or a couple of them. I am not sure about the concrete architecture, but it doesn't matter. Then you train using the SMUDLA or SDUMLA data set. You train on those embeddings given by the CNN these last layers. And those last layers will realize that this is not important, that this is not important, and whatever is not important or it is important. They will learn on that. So whatever is not important will have a final, I do not consider you. And whatever is important will be considered by these last layers.
I agree, but I was more thinking of what if there's something that we consider to not be important, but the model doesn't.
Yeah. That happened. In this case, it is not the case, because the background is always the same. There are things which are very well done in this data set. So there are no these ambient noisy thingies. That would happen, for instance, in these faces in the wild data set. And they did a funny experiment, just putting a black blob on the face of the people and recognizing them. And this experiment got basically the same results as the state-of-the-art face recognition algorithms. Back then, not nowadays. But anyway, it was such a surprise. And they realized that indeed the classifier was paying attention to things in the background that were characteristic of that person. And nobody would think about that. But this is not the case, because the background is always the same for everybody. The reading units are either the same or equivalent, I don't know. So the images are good. It is well prepared. It is not like face images where that could happen, and it has happened. Please?
The background is the same, but perhaps the finger width might not be, right? Because if you press more, then like the width of the finger...
Yeah, there will be some differences.
Into account, and it will classify it as like it will come up with different features. Right?
Sure. Or it could be slightly rotated with respect to previous position. Yeah, but your algorithm should cope with that variability, with a natural variability. And that is one of the advantages of using user-specific approaches, that it knows that, for instance, you are very consistent and you always make good positioning of the finger, etc., but I am not doing the same. So my template will have a smaller key, probably, etc. That will happen, and your algorithms should be able to cope with it. Yeah? Please?
So a brute force attack would consist of bringing a suitcase with 2 to the 37 3D printed fingers with veins in them, and then just inserting them one by one.
Yeah.
Okay.
No. Well, you can do that in many different ways. And for this system, indeed, you should just try this 2 to the 37 different keywords, code words. So you just generate different messages, and at the end you get whatever. That is the length of the message you input to the error correcting code. So you can brute force it. How practical that is? I think it can be done. It can be done in some cases, but in those cases you would never only rely on this for authentication. If you can do a brute force attack, you should go to higher security standards. I think the last ones, these ones with more than 100 bits, okay, good luck, brute forcing it. Yeah. But even if you have as few bits as 12, you could use it. But no brute force attacks, please.
Well, not ones where you rip out the sensor and connect your own.
Yeah, okay, but that is not my job, I mean. But for sure, your system should not be susceptible to be to get many consecutive authentication attempts by any user. That should be detected, the credentials temporarily revoked or whatever. But that is, let's say, part of the security chain. But I mean, you just need to know what you're working with. Okay, any other question? So thank you very much.